All right, I'm doing my best to control the glare. Again, still trying to get used to this new camera. Hopefully I will get better at it as I go along. So these notes are on the three distinct ways that we describe location. So the last lecture, the last little bit I talked about the ways to tell the difference between a scalar and a vector. So if we recall that a scalar was just a magnitude and a unit. So it was just like 35 centimeters or 20 pounds. A vector had a unit, a magnitude, a unit, and a displacement. So it had a number like 10, a unit, kilometers per hour, and a displacement or an area it went, which would be west. So we're going to talk about the three ways we describe location in physics and the symbols that we use for all of them. So the first way we describe it is by distance. So distance is the total length of the path traveled. And when we talk about distance, we don't care what direction it goes in. So direction doesn't matter. We just want to know how far total they went. They went 50 kilometers. They went 20 kilometers. This is a scalar quantity. So that's important. Distance is a scalar. Direction doesn't matter. Direction is what divides a scalar from a vector. And if direction doesn't matter, then it has to be a scalar. And this is like what your car odometer reads. So like your odometer in your car tells you how many miles you've gone, or it tells you how many miles you've gone. For instance, like you've gone 80 kilometers or 80 miles. The symbol that we're going to use is just a letter, just a lowercase d. That's it. So the next thing we need to talk about after distance is the position. Where is it located? So the position is the location of an object. I didn't mean to grab purple, I meant to grab red. And they're all showing up the same color for y'all. The location of an object relative to a reference point. So it's a vector quantity, because if we're looking at a reference point and we're referring to that reference point, we're going to say that she's 10 miles west of something. I live about 2 miles east of the school. That's my position. That's where I'm located. So, for instance, if we go back to that car, our example for a position could be that it's 25 miles west. Remember, directions go in brackets of the library. I doubt many of you even go to the library anymore, the public library. I don't even know if it's opened up again, but hey. I said the position was the location of an object relative to a reference point. My reference point in that example is my library. That's what I'm comparing it to. That's what's not changing. It stays the same. Another reference point would be like a tree. Trees usually in the same place all the time. A house would be a reference point. When we write a position, because it is a vector, we're going to assign it a letter, usually the letter D. And vectors like to wear their hats. They don't want to go somewhere without their hats. And if they're going in a certain direction, they definitely need a hat on to make their appearance in public. So vectors always have a vector hat. And this is our symbol for position. Last different way we're going to use to discuss a location of something or to describe the location of something is displacement. This is a really big one. This is where we're going to spend most of our time talking. Displacement is a change in position. So it's where you went. She left the house and went 5 miles east to the neighbor's house. It's a vector quantity as well, because I can't tell somebody where you went unless I tell them what direction you went in. If the police asked you where somebody went and you just said, she went that way, well, what's that way? So displacement, an example of displacement would be a rabbit hopped or the car drove from a starting point 5 miles east of a carrot to 15 miles east of the carrot. And that's not miles, that's meters. I've been in physical science going back and forth between English and metric units way too much. In science, that's a lot to write. And if you're like me, you don't want to write that much. So we like to abbreviate things. So we're going to use this little symbol over here. This symbol that I'm going to draw is called a delta. And a delta means change. That's a really shorthand way in science that we can abbreviate the change in something. So when we write the symbol for displacement, we are going to put our D. We're going to give it a hat because it's a vector. So we have our position, but we're not just talking about position when we talk about a vector quantity. We're talking about a change in position. So I'm going to put my delta sign in front of it and make sure my hat's on there. So I've got my symbol. I've got my triangle or my delta, which means change. That D stands for position. I've got my hat, which is my vector hat. So that tells us everything we need to know. It tells us that there's been a change that's occurred in a person's position. We know what direction it's in because we have a vector quantity. In order to find displacement, you're going to use a really simple equation. So displacement is equal to position 2, or their final position. You'll also see this written as with an F next to it. So you can write it with the number 2 or with an F. I know that's hard to see with the markers, but one has a 2 and one has an F, and it has minus D1, which is their initial position. Another way you'll also see that written is D with the letter I. Let's see if I can zoom in for you. Ooh. There we go. So you'll see it written both ways. It just depends on who is writing it. I tend to prefer the final minus initial so I don't get confused and think those are subscripts. Some people prefer to write 2 minus 1. It all depends on your personal preference. And what your preference is your preference. And I'm not going to fault you for that. That's how you see it better. So let's take this and apply it to a problem or apply it to something that we could learn. It says Xavier travels to Yvonne. How far does Xavier travel? And what does this value represent? Okay, so let's take a look at what we've got. We've got an image of where Xavier lives. So Xavier is going to start here where the X is, because that's Xavier. He's going to walk 110 meters. And then Xavier is going to walk 70 meters. So it just wants to know how far Xavier traveled total. So total, Xavier traveled 180 meters. And then it asks us if this is a distance, a position, or a displacement. What does this value represent? Well, it doesn't tell us what direction Xavier walked in. So it can't be distance or displacement. It can't be position or displacement because those are both vector quantities. There's only one thing it can be. The only thing it can be is a distance. So the only thing this could possibly represent is distance because there's no direction. So it's a scalar. The only scalar we have is distance. All right, now we are going to throw a little bit of a loop in there, and we're going to bring some math back. So it says, if Xavier was a bird, how could he get to Yvonne? And what does this value represent? So if Xavier is a bird, he's not bound by the human laws that we have to follow a road. So if Xavier was a bird, he's going to take the shortest way to get to Yvonne, and he's going to cut across the middle. So he'd travel there in a straight line. Now we've got a problem. We got to figure out what this straight line is. So we're going to bring back a little bit of geometry to figure out how we could get there. So we're going to use the Pythagorean theorem. And a squared plus b squared equals c squared. If you don't remember that, you can always go back to your formula sheet, and it is definitely on there. It's definitely on there in this first chapter. It's one of the formulas I provided for you. So we know that the first leg of the trip was 110 meters. So we're going to have 110 meters squared. The second leg of the trip was 70 meters squared. And we're going to equal that to c squared. So when you do your math, you're going to come out that c is equal to 130 meters. But that doesn't tell us enough, really. So now we know this is 130 meters. Okay, 130 meters in what direction? How did he get there in 130 meters? Did he go 130 meters south, 130 meters east, 130 meters west? And there's not a compass on this map anywhere. So we can't tell you that because we don't know what our relationship is with this map. For all we know, down here could be north and this could be south up top. So now we're going to pull out a trig formula. And we need to figure out what the angle of theta is. And this is our theta right here. So we're going to pull out the tangent of theta is equal to the angle opposite over the angle adjacent. So we're going to get that theta is equal to 32 degrees. So now I know a distance. So I have a magnitude, I have a unit, and I have a direction. So my final answer is going to be that the displacement was 130 meters. And for the sake of this problem, I'm going to assume our compass goes like normal. So he went 130 meters east, 32 degrees north. Because we have all three, we're going to consider this a displacement. For right now, if that math is a little bit over your head, it's completely fine. I promise you when we get to the next grouping, I'm going to spend a lot of time going over all of that math and how to solve all of those math problems. For right now, the main thing you need to understand is that that was displacement because we had a direction. Last but not least, we're going to the raceway. We're going to the racetracks. It says a raceway is designed as a loop in which one lap is 4 kilometers. All right, this is the focuser. There we go. If a race car completes 200 laps, what is its distance traveled? So the best thing in physics to do is to start out with a drawing. So we know that it's a loop, so I'm going to draw a circle. And one of those loops we know is 4 kilometers. And our lovely race car driver, we're going to have the same race car driver all semester. Trust me, he's going to drive a lot of cars by the time this semester's done. We're going to change his uniform up a little bit, but he's going to drive a lot of cars. So we know that each lap is 4 kilometers. And we know that he went 200 times around that. So his total distance, his D, is equal to 800 kilometers. The position at the race car relative to the starting point. I don't know if you've ever watched race cars, or you've ever watched them race on the track, but the start line is usually here. It's like when you run a horse race or you run a physical track race with a person and you go around and around and around this loop, but you start and end in the exact same place. So his position at the end of the race relative to the starting point is 0 kilometers. He's in the exact same place he started at. The last one wants to know what his displacement is. So what is our race car driver's ultimate displacement in this race? How far did he finally go? Well, his distance was 800 kilometers. His position never changed. So his final position minus his initial position is 0 kilometers. So even though the race car traveled a distance of 800 kilometers, technically his displacement or his change in position, there wasn't any change in position because he ended up exactly where he started. So it's possible to have an extremely large distance traveled, but to have 0 displacement because you ended up back at the starting point. After this, you're going to work through some PowerPoints on your own and some problems on your own, and we're going to apply this to some straight vectors where all you have to do is add them together like we did up here. There's not going to be any more of this trig math involved in what you're doing on your own today. So as long as you can add and subtract, you will be good today. If you have any questions about any of this, please feel free to contact me, and I can answer any questions or work through it with you.